Okay, so hi all. Welcome to the second video for this week on solving PDEs, in particular solving the heat equation, which will have a triumphant moment today in this video, where we do finally get a solution to this thing that's taken a while to even understand, I think. So let me just start right into this then. So in the last video, I think we stopped roughly here. I think maybe one more slide, but which was to look at the heat equation, which is here. Sorry, which is a PDE, our very first PDE given up here in the box, where of course this would say that u, which is our mystery function, is a function of x and t, two variables, and apparently heat transfer or heat diffusion, as well as many other kinds of diffusion, is governed by this general idea saying the first t derivative, that's ut, is proportional to the second space derivative, as this might be called, or x derivative. So that's the relationship that we at least loosely explored, right? I'm not doing a fancy crazy proof of why this actually holds up, but let's at least say that we trust people that have been using this for a long time to model heat flow and heat transfer, that this is accurate. But at least it sort of made sense in our example that we looked at last time. This alpha squared is just a constant, and that it's the constant that describes how quickly does this material, whatever it might be, transmit heat, or in other words, how insulated, maybe is a good word, human word, to how insulated is this material, so how readily does it allow heat to move across it. A higher value here indicates heat moves fast, a low value means it moves slowly. So that's the model, that's the equation, that's the PDE. We roughly stopped here with an idea of saying, well, all right, that's a DE at least. We have lots of practice solving DEs. But what does an ODE usually have? It also has an initial point or points. So how does that look in PDE world? Well, rather than giving you an initial point or a couple of points, that's not actually going to be enough to describe the initial situation, right? What do our usual initial values tell us for an ODE? Is it gives you everything you need to know about what's happening at time zero, and then of course you use that in order to solve for what's happening in the future. Well, at time zero, what's happening to this rod or this bar? Well, there's a whole bunch of stuff that's happening because it's an entire length of metal. So in order to describe what's happening initially, I actually have to give you a function, because of course I have to describe the temperature across the whole bar at time zero, not just in one or two places. So my initial information, which is usually called an initial boundary condition rather than an initial position or initial value, it's usually called initial boundary or boundary condition, is because I'm going to describe to you the initial temperature all along the, in this case, the rod or the bar, right, which is the boundary of the problem, so to speak. Okay, so that's getting us sort of set up with our usual things. I just gave you a little example of what, and we use little f of x to describe this boundary condition, this initial temperature profile. So I drew you a cute little picture of a temperature profile example where maybe the middle is very hot, but the ends are not, right? And we're going to always assume that the edges have temperature zero. We're going to assume that they're the same, and since we're assuming they're the same, why don't we go ahead and assume that they're zero? Since if they're not, we're just going to shift our solution anyway. So let's make our lives easier and say the zero on the edges. And I have some function, I just made this one up, but some function that describes the initial temperature. So then, of course, the goal is to say if heat is governed by this, so this is now the full heat equation setup, how do we solve this? So I'm going to just draw you one last cute picture, and then we will get to the answer, just in case again. Because I do think that when we go to, much like in Calc 3, or really even Calc 2, but in Calc 3 especially, once you sort of go to a higher dimension, we lose a little bit of a, well, what is this really that we're doing here kind of thing? So I don't want you to feel like this is just total arbitrary nonsense that, okay, I'm just going to fake this and hopefully get through this. I hope that you have some decent understanding of this is still regular math and still regular functions and things like that. So let me just give you one more picture before we get to the solution. So a good way to envision this whole process, this whole process of solving really any PDE, but I'll stick with the heat equation, is usually drawn, and if you go to any sort of description of a PDE being solved, you'll get a picture that probably looks something like this, or at least starts like this. So what is it that we as the solvers are trying to do here? So I'm drawing for you a picture here where I'm going to describe where on the left and right sides here, I'm going to consider these to be t-axes. That's a little funny, of course, to say that, because usually we think about time or a t, or whatever variable is having a single axis. But this is just a mock-up picture that I'm doing. So let's imagine that time flow is vertical. So in other words, this is time 0, and then time 1, and time 2, and so on, right? Right? Same on the other side. Okay, right. So in other words, as I would consider this problem, if I'm trying to draw you a little drawing or a visual aid to help you understand what we're doing here, I might imagine that time is flowing from south to north, I guess, right? So in other words, I'm considering what's happening to this rod. So here's my rod. Okay, I'm sort of on purpose not drawing it super clear to look like a rod, because I just sort of want it to be a line at this point, really. So, of course, at time 0, this f of x character that we've been talking about, that's the initial temperature, you could call it profile. It's also known as the boundary condition. But in other words, it describes the temperature across the bar at time 0, just like we just did in this last example. Now, I don't know how much this is, so I'm just going to make something up here and say, let me switch to a different color, like blue here. So f of x, the thing that we're given, is maybe describing the initial temperature. I'll pick one that's sort of similar to the one I had a minute ago. That's f of x. Now that lives down here on the boundary, because of course that's at time 0. I already know the temperature profile of this thing. It's hot in the middle. Here, let me exaggerate that a little bit. This is a bar that's maybe hot in the middle and cold on the ends. That's my initial temperature profile. So that's given. And the the PDE, and I'm sorry, one more thing I'll label on here for you, is that, of course, this is the left side of the bar and this is the right side of the bar. So this is, let me switch back to red. So this is x equals 0 is here. And this is x equals L. That's the other end of the bar. So, of course, we know this first one, f of x. That's the temperature profile. So our ODE, which is usually kind of just as a reminder to the author or to the reader, is here, just sort of in the box somewhere to say, that's governing, this PDE is governing how heat evolves or flows over time through this process. So I'm starting from this picture where I know several things. I know the initial temperature is 0. Other things that I know about temperature is that I know on the boundaries the temperature is actually always going to be 0. So in addition to knowing that, because that's our assumption, is that over here and over here, that no matter what time we're at, we're always going to be assuming that U, the temperature on either end of the rod, is 0. So sometimes we'd write that in here just to remind ourselves. And in that sense, we are aware of what's happening. Part of the reason why these are called boundary value problems is that we're aware of what's happening with temperature on the left, the left side, the right side, and the bottom side is how I might call this time 0, right? That's the whatever's filled in as my initial one. The thing I don't know is what's in here. And that's all governed by this PDE. So the PDE is what informs us. Here, let me do, just one last color here. So red is just my framework, my labels. U are my initial things, or things that I know are true about my solutions. And then the PDE is what tells us everything else. So I'll go to green here, so this is green. Then the PDE, let me do that here. That's what tells me how to evolve from time 0 through this whole process. And I'm making these up, right? But maybe what happens, maybe this is an example where you heated it up and then you turn the heat off. So I don't know, it might sort of do something like this, where it's gradually slowing down. And then maybe after another minute, it's almost flat. That's maybe time 2. And then maybe at time 3, it's actually like pretty much flat, and you just have a little blip laugh, okay, and stuff like that. The PDE, that's what's the green stuff I just did. That's what the PDE is telling you, which of those is right, in other words, right? So our solutions, when we end up coming up, I mean, we should all be a little bit like, I don't even know what a solution to this thing is yet. It's these green graphs. And they're all going to, as long as these guys satisfy the PDE, I will have found a correct solution to this. All right, so before we get into the what the heck crazy process are we about to do in order to solve this thing, let's at least take a minute to appreciate what are we even trying to come up with. And the answer is we're trying to come up with some representation of how this heat evolves over time and space, right? So in other words, if I had stuff like these green graphs that I just made up, but that's what I'm shooting for, is to be able to say, oh, heat evolves like this. Because of course, just like any science problem, I want to be able to predict the future. So I want to be able to say, after 2 hours, what's going to the temperature profile look like? Oh, I guess it looks, if my picture's right, it looks like this. How about after 5 hours? Okay, well, it looks like whatever your solution would be at time 5. Okay, so that's our goal, right? So our goal is to come up with the green. All right, the blue is given. Right, so I know you, okay. So, so let's get you how to do that then. So, solving the heat equation. Okay, which I will just write down here. So ut equals alpha squared minus x. And with f of x being our boundary condition, or our initial boundary condition. So that's u of x at time 0. And this is all living in the domain x between 0 and L. Okay, so that's our heat equation there. So 99% of the times, how do we solve how do we solve a DE? Is we do our favorite thing. We make a guess, we plug it in, and we hope that we're able to force a solution to appear in front of us. And then we're going to do the same thing here. All right? So if I'm trying to solve this, let's make a guess. So let's guess that our solution is separable. Oop. Now, separable is a word we use like a million times in math to mean probably a whole bunch of different things. So what do I mean in this case by separable? I mean, let's guess that our solution, right? Let's guess that a solution can be separated. Now, a function of x and t, of course, simply means that I have x's and t's over here. But a separable function would be one where I have x's and t's, however, you can neatly separate them into some x's times some t's. Now, of course, that's not true all the time, right? There are many functions of two variables that are not separable. But if you were going to try to guess a solution and you were trying to guess the easiest thing, or something that might have nice properties, this is a reasonable thing to guess, because it's, as you might imagine, I'm heading towards trying to basically say functions of two variables are like crazy hard to do stuff with. But functions of one variable, we're like super experts in doing those because those are ODEs. So if our hard crazy function is actually just the product of two easy ones or easier ones, I might have some hope of transforming this PDE into some ODEs, in which case I can fall back on my previous knowledge of ODE solutions to solve. And that's exactly what's going to happen. All right, so let's go. So here's our guess. So as always, what do we do with our guess? We plug it in. We plug our guess into the PDE. Of course, that's this guy up here. And what do we get? Well, ut, remember that's the t partial derivative. Oh, okay, well if this is my u, which is my guess, I should say, this is my guess for a solution, the t derivative of this, hopefully we would all be able to say very easily. I'll do this out the slow way. So by plugging it in, of course, I mean, let's take our guess and run it through the PDE. Right? So our guess is that our solution is actually this. So if we, let's do it that way first, right? So I'm just plugging it in to see what shakes out, basically. So if I plug it in, this would be my, this is me just plugging this in, of course. And of course, I want to make sure I'm reminding myself that if I'm looking for a solution, I'm looking for it to work for all t and for all x's, or you could say for all pairs of x's and t's. I don't know why I did t first. It doesn't matter, but since we listed x first, sorry. So for all x's and all t's, right? So any pairing of those, within the bounds, right? Obviously, x between 0 and L, and t being from 0 to infinity, right? Time. Okay, so now these, of course, I can say something about, because, of course, this is a t derivative. Oh, well, if I'm doing a t derivative, g is just a constant. And, of course, what's the derivative of h? Well, last time I checked, it's h prime. Okay, so I'd be saying that has to equal, and now on the right side here, same thing. Alpha squared, that's a number. And then here, the xx derivative, well, this is a function in terms of x, but this is a constant, because x derivatives, right, t stuff is just a constant. So I'd end up with h of t. And then I would do the x derivative twice. So how about that? And again, I'm just going to remind us that has to work for all x's and t's. Okay. Well, this is still bad. I don't see a solution. But let's at least comment that before I even do anything else, this is looking a little more like ODE land, where I have just a nice regular function, and this is a second derivative, and I have some other nice regular function and a first derivative. Now, I'm not super excited about the fact that they're both present, so why don't I do a little bit of organization here, and I'll move the h's to the one side and move the g's to the other. How about that? So I'm just going to, in an attempt to get ready to solve, put the h's over here. So I'll put the alpha down here too, just for fun. Now if I put the g's over here, I'd have that. And again, I'll keep copying this down, but this has to be true for all, maybe I'll leave yourself a little bit of space there, for all x's and t's. Okay. I mean, this is looking a little bit like I've done separation of variables from ODE's class. A little bit, not quite, right? And that doesn't really work for a second derivative anyway, but, So let's read this to ourselves left to right, and then if we were in class, I would ask somebody to make a clever observation, but I'll just make it for you. But let me read this left to right. Okay, so what's this saying? So we made a guess, and as usual, we plugged the guess in. And as usual, our guess only becomes a truth or a reality if whatever is being forced by plugging our guess in to be true is actually true. In other words, for our guess to actually work, I would need the g and h that I'm guessing as my guess to satisfy this line, also this line, also this line. Right, okay, duh. But what does this last line say? Okay, this last line says, your mystery h has to satisfy that if you did the first derivative of h and divided by h itself and also divided by this number, that would equal your mystery g below the second derivative of your mystery g of x. But this would have to be true, when I read this from left to right, for all combinations of x's and t's. I'll go ahead and underline that one more time. So what do I have over here? Now this is a statement about t's. This is a statement about x's. Right? I mean, that's what it means to say you have a function of t or a function of x. So in a real life example, this would be a bunch of t's, and this would be a bunch of x's. So when's the last time you had something that had a bunch of t's in it equal to something that has a bunch of x's in it, or I should say that could have a bunch of x's in it, a bunch of t's, a bunch of x's. They're the same as each other for every combination of x and t that you could ever think of. So x equals 1 and t equals 5. Got to work. X equals 5 and t equals 1. It's got to work. How could you ever have something like, this is just a for example, how could this ever turn into that and have this be truth? You could never do that, because I have to make sure whatever I've written down with these two circles has to work for every pairing of x and t that you could dream up. So the claim here, which is really important to understand, is that while this could have, this is a function of t, and this is a function of x, the only way that a function of t is always equal to a function of x is if both functions are simply constants. I could never have any actual t's here, and I could never have any x's here, because how would I always get them to line up? You could never make that happen. Even if you had a constant here and x's here. How is 5 equal to x squared for any x that you can dream up? It isn't. The only way you could get this is if maybe this stuff simplified to a number like 5, and this stuff also simplified to the same number. Now could I say left-hand side equals right-hand side for any combination of t and x? You bet I can, because 5, last time I checked, is always equal to 5, no matter what value of x or t I might be picking. Now this seems a little funny, right, because it seems like I'm cheating here, in the sense that, of course, I'm not actually using these x's and t's. But remember, I'm making a guess here, and all I'm doing is exploring what would have to be true in order for my guess to work. Maybe this is going to lead us to an impossible situation, and this was a terrible guess, and I've wasted 15 minutes of your life that you could have been Netflixing. It's possible. Okay, but probably I haven't done that to you. So we're going to keep going with this, and I'm going to say this, right? So these guys, the only way to make this happen is if both of these are just constants. In other words, while you're allowed to have t's here, and while you're allowed to have x's here, you're never going to get these to line up unless this is equal to a constant. Okay? So I'll say, go ahead and replay that if you didn't get that, but that's an important piece, right? So do make sure that you understand that. All right? So, if that's true, I'm going to go to the next slide now, but if we've convinced ourselves, which hopefully I have convinced you, that for this to equal this, they both have to be just a number. Now, I don't know what this number is yet, but I think I could then say, oh, well, now I could say that means this guy has to equal that number, and this guy has to equal that number. And believe it or not, those are going to just turn into simple ODEs. All right? So I'm going to go to a clean slide here so I have space to, I'll reproduce this though. So, I lost the okay. So for our guess to work, we must have that this expression that we had on the last slide, h prime over alpha squared h, has to, in order for this to be equal to the other one, they both have to be equal to some common constant. Now, in the strange world of labeling, we're going to call this constant negative sigma. That's a lowercase sigma there, the Greek letter. All right? So it has to be true that these are equal to each other and that they're both equal to a constant. So we're going to call that constant negative sigma. So let me write that down. Where sigma is known as the separation coefficient or constant. I'll go with constant. Okay, it's a number, right? So it's I don't know what it is yet. But I know that in order to make this last line in our last slide, to have it make any possibility of being true, those both have to be equal to just a c, a constant. And instead of calling it c, for reasons unknown right now, we're going to call it negative sigma. Okay. Obviously, we're probably calling it negative sigma because we're going to try to, well, anyway, you'll see why when we finish this. Okay, so this is huge. This is hugely important because now, what do I know is true? Well, remember, my goal was to make our guess. Oh, that's where that went. My goal was to make our guess work. So what was our guess? Was, of course, that a solution would be g times h. Well, what have we now revealed is that g times h, in order to get the right g and the right h, the g and h you need are the ones that make this work and that make this work. But if you squint at these are both just regular ODEs. Okay? So to get the correct h and g, we simply need to solve these two ODEs. I'll put an exclamation point of happiness, right? These are just, each of those is just an ODE. And if we could solve those, we smash them together, and that becomes the solution to our PDE. Okay? So we're going to do these one at a time. We'll do a little bit of exploring on what H is first, and then we'll solve, well, okay, we'll sort of work a little bit on both of them, I guess. How do I want to start? Okay, so this is our goal, right? So our goal for probably the rest of this video is to come up with a way to solve those two ODEs. Okay, so I'll write them down in a nicer format. So to solve these two ODEs, those two up there, I don't particularly like them as fractions, so how about I just rewrite them in the usual format that we see our ODEs. So the first one, of course, if I rewrite it and swing this to the other side, might be H prime. When I move this to up here, I could certainly do that, and then when I move it over to the right side, to the left side, it becomes plus sigma alpha squared H equals 0. Right? That's just me rewriting this first one. So maybe I should number these 1 and 2. Right? So 1 becomes renumbered as relabeled like that. And 2, I'll just do the same idea. G double prime. If I multiply g of x to the right side and then move it back to the left, I'd have plus g of x equals to 0. Now these are both homogeneous. I have 0 on the right side. This is a first order homogeneous. You know how to solve this in week 2 of ODE's class. This is the second order homogeneous. That's just a constant. That's just a constant, right? You knew how to solve that in week 7 or whatever of ODE's class. So we're going to know how to solve both of these. But I wrote them this way to point out a little bit of a something, which is that in order to actually solve these completely, as we know, I'm going to probably need initial values for each of these. So in other words, why did I leave a big white space over here? It's because usually, don't we have something like this? Right? And in this case, I probably would like to know h of 0. And in this case, I'd probably like to know g of 0. But it's a second order ODE, so I'm going to need to know 2 facts about g. I'll leave it vague as to what the second fact might be, right? But I know that to solve ODEs and to solve for the constants, I need to know 1 fact for a first order and 2 facts for a second order. Aha. So where am I going to go to get some of that information? So I'm going to fill these back in, but I need space to show you where these come from. Well, a couple of observations in order to get us some good data to fill in there. One, so I'll say, 1. When x equals 0, which of course means I'm on the left side of the rod, or the bar, we've insisted, or we know, or we're assuming, that u is 0 for any time t. So what does that mean? That means that you get 0 if you do this for any time. But in our guess world, remember u is actually g with g times h, right? So that would mean g of 0 times h of t would have to be 0 for any time t. Well, look at what this says. This says you get 0 when you do the product of those two for all time t. Well, how could that happen? Well, either h of t could be 0 for all time t, I'll go ahead and let you fill in why that's crazy. Okay, I'll just leave that for you to think about. But if h was 0 all the time, in other words, h of t is just legit 0, I'm pretty sure this guess that we're trying to work on is going to be a dumb guess. Okay, so that can't be true. So it must be then. So either that's true, well, but that's crazy. Or how about g of 0 is 0? Oh, well, I like that, right? That's not crazy. Oh, so look at that. With a little bit of thought, we get a condition that says g, our mystery g, at time 0, at position 0, is 0 degrees. And I'll say similarly, just do the same argument. On the other end of the bar, g of L is also going to have to be 0. Okay? Same idea, just repeat this argument, but replace 0 with L, and you'll get the exact same conclusion. Oh, well, look at that. These look like initial points for my mystery g. So I'm going to go backwards right now and say, oh, here's my ODE for g, and we just showed, I'll draw a little line here, that these two facts have to be true, and I bet this looks now like a complete second order ODE that we could solve. So maybe let's do that. We'll come back, I'll fill in the h of 0 situation. So what do we think? So let's pull apart 2 then. So let's focus on that one, since we've got our initial conditions. So how about let's solve the g of x ODE, which I'll just recap for you here, right, is g double prime, the second derivative of g, plus sigma g equal to 0 with, and now we have our 2 initial conditions that we just discovered, g of 0 is 0, and g of L is also 0. I know usually for a second order ODE, we had the value of the function at 0 and the value of the derivative at 0, right? Those were our 2 usual points, but that was actually just more so in order to say, well, I probably know what's happening at time 0. But as long as you have any 2 facts, it doesn't have to be one is about the function, one's about its derivative, any 2 facts will let you solve for C1 and C2 at the end of the day, right? So this is perfectly fine. So we want to solve this thing. Okay, well, this is the second order ODE, which I'm pretty sure means we solve this in the usual way, where we would look at the roots of the polynomial and see if we have maybe 2 complex roots, 2 real roots, or 1 repeated root. So we're going to proceed in a somewhat similar fashion of doing some cases here. But instead of doing it exactly like that, I'm going to instead say, let's consider, So let's consider three cases. Because we know nothing about what this sigma is. Let's consider a very silly case first. What if sigma was 0? Well, if sigma was 0, then my ODE would just be this, right? Obviously, if sigma is 0, it kills this, and so we'd be here. Now, we don't need any fancy math to know what's the solution of the second derivative equal to 0. I mean, if you want to, you could say, well, if you integrate once, you get a constant. If you integrate a second time, you get a line, right? Or, okay, if you don't like that, we can sort of do this for real, right? So this would become my ODE. How do I solve this? Is I would do an integral once. Oops. Okay, the integral of a derivative undoes a derivative, so I'd end up with g prime equals, what's the integral of 0? It's a constant. And now in order to solve for g, I do one more integral. So I'm going to say, now let's integrate again. Maybe I should write that down as a separate line. So if I do one more integral, now I'm to g. Oops, sorry. What's the integral of a constant? Well, that would turn into c1 times x, and of course I'd get a second integration constant. Okay, now of course that's just the equation of a line there, right? Okay, so far I don't see anything disastrous, but we're about to. Okay, well let's solve for c1 and c2, because, you know, we got these initial points that we could use. So, okay, so if I do this, let's see, so I'm supposed to get 0 when I plug in 0. Okay, so that tells me C2 is 0, right? Okay, so I'm halfway there. And now let me use my other fact, which would say I'm supposed to get 0 when I plug in L. Okay, so C1L plus 0, right? C2 is 0. I just already showed that. Okay, so C1 times L is 0. Aha, so the product of two numbers is 0, which means one of them has to be 0. But it's silly to say that L is 0. L is the length of our rod. So unless it's a magical rod that is of length 0, meaning it's imaginary, I'm pretty sure the only way this is true is if C1 itself is also 0. Right? L can't be 0. That's the length of the bar. Oh, awesome. Okay, so what is my solution? Bringing those back in. So g of x is 0x plus 0. 0. Uh-oh. So I shall once again ask you to think. If I come up with this wonderful solution to my PDE, which remember was h times g, and g is the I'm always 0 function, think about what that might say about our guess, right? So once again, I'll mark this as silly. Can't be. You can't have g being always 0. So I think this whole case is also silly, right? So I can't have that this mystery sigma, that can't be 0. Okay, so since that's not an option, case 2, well, I don't know, let's take the other two cases. So it can't be 0, so I suppose the other two cases might be that it's negative or that it's positive. Now I'm not going to do this case, but I'm going to tell you that this case also results in a silly, or if you don't like my use of the word silly, impossible situation. And I probably will ask you to do that on some future assessment. Okay, but trace it through, and you'll come up with a similarly, nope, that never happens, or nope, that would lead to just a nonsense answer. Okay, well, gosh, I'm running out of cases here. Now, if we did the third case and that was also silly or impossible, what would that mean? That would mean that I've deduced an impossible guess, or in other words, I've proposed a guess that simply is never going to work. And again, we run now into the, I've wasted 40 minutes of your life rather than 10 or however many it was earlier. But since I'm not into wasting your time or mine, this case is going to yield a fruitful solution. So this case is going to be just fine. So let's run this one through. So this one, let's do it. So if sigma turns out to be a positive number, then once again, I'll just repeat, the ODE is right here. G double prime plus sigma G equals 0. Right? That's our ODE. With, I'll repeat the whole thing. With G of 0 equals 0 and G of L equals 0. Right. Okay. Now, so if I'm really going to solve this, now we're ready. We're ready to solve this. I'm going to do this in the ODE style of saying, well, that's r squared plus sigma equals 0, right? There's no g prime term. That would be the r term. Okay. So that means r squared is what? Negative sigma. Now, since sigma is positive, negative sigma is obviously negative, which means I'm in a situation where r is going to be imaginary. Right? R is plus or minus the square root of negative sigma. Right? And how much is that? Well, since I know r is positive, this is negative, which means I could write it as plus or minus root r times I, because I know that that under the square root, right, I know that that's negative, because sigma is positive. Right, that's the case. That's the only legit case anyway. Mm-hmm. Oh, I'm sorry, that's a sigma there. Not an r, sigma. Okay, and of course we remember from back to ODE's class, what happens when we got a complex root is that our solution had cosine and sine in it. It's the same thing that we've even been doing this semester, right? So I got two roots, they're complex, and I won't recall this all for you in any great detail, but remember from ODE's class, that means the solution is, maybe I'll make enough space here. Okay, I'm actually just going to go to a whole new slide, but keep going with this. So from ODE's class, the general solution is G. So C1, and if you remember, don't write this down yet, but if you remember from ODE's class, it was this e to the AT cos BT plus the same thing with sine. But A was the real part of the root, which is 0 for us. So it's actually just cosine. Right? So I have nothing over here. That's the A piece. Well, I don't have anything there. That's B. Okay, so A is 0 and B is root sigma. So I end up with cosine of, now this is one of our least favorite things to probably write, but bear with me here. And then the same thing but with sine. Oh, I'm sorry. These are x's, not t's. So used to doing ODEs here, because we're doing g of x, right? Okay, so this is sort of exciting that we've gotten a solution. Now that's not a solution to the PDE, but that's half of it. But let's run our initial points through, right? So, and of course, remember, we also know that's our general solution. So now let's run the initial points we have through this and see if we can make heads or tails of who these things, of what C1 and C2 might be. So of course, let's use our two initial conditions, using g of 0 equals 0, and g of L is also 0. What do we get? So if I do g of 0 equals 0, what does that mean? Well, if I run 0 through this, remember sine of 0 is 0. So sine of 0, so it's going to kill off the C2. Cosine of 0 is 1, so I'd get C1 is 0. Okay, I'm getting a little nervous now, because of course that's what kind of happened in our silly case. So if C2 also turned out to be 0, I'd be in trouble, because once again I'd be in a situation where I'd say, so my mystery g has been the 0 function. Ugh. Okay, but that's not going to happen. So on the one hand, this is 0 though, all right? So that means, of course, g of x. I'm clearing this out now. I just have this piece. Okay, let's try our other initial value. Our other initial value says that you should get 0 when you do g of L. Oh, let me do it that way. Well, what do I get when I do g of L? Well, I don't know. I get C2 sine of, sorry, there was supposed to be a square root there, root sigma L. Okay. So, all right. So how much is C2? Well, I have options here, once again. How could this be true, this line right here? Well, I have one thing, that's C2, times another thing, which is this sine character. Okay. Well, how would this be 0? Well, on the one hand, C2 could be 0, but once again, that would lead me to that my solution is just nothing. So I don't think that's not the option I want to choose. When is the other situation where this could be 0? It could be that this piece is 0. So how do I make this true? Is we're going to choose, because I don't want to just clear out my solution by making C2 0. We're going to say, this will be true, provided that this piece is 0. Sorry, I'm having trouble writing square roots. Okay. Okay. So when is that true? Or what has to be true in order to make this happen? Now, remember, L is a number that you know. L is physically how long is this rod or this bar. So that's fixed. I can't do anything about what L could be. L is whatever L is. Sigma, on the other hand, remember, that's this separability or separation constant. We just made that up. We just made up that lettering. I don't actually know how much sigma is. So, but what am I saying here from top to bottom? Our guess works as long as this is true. Well, how do I know if this is true? Well, think back to trade class. How do you know the sine of somebody is 0? Well, what has to be true about that somebody? If you remember, hopefully, a little bit from trig class. Sine of every pi, every multiple of pi, is 0. So when is this true? So this is true provided that this is true. And when is this true? Well, sine of any multiple of pi is always 0. Sorry, maybe I should use n since I'm about to use n. For any whole number, even negative ones, right? So I have to make sure that these are the same. So, put these two facts together, and what do I know has to be true? We must insist that square root of sigma L has to be a multiple of pi. So therefore, square root of sigma has to look like that. And this is for n equals 1, 2, 3, and so on. Any whole number. Right? All of these work. Okay, so we're ready for a solution, believe it or not. So G, which is this is the general solution. We eliminated the C1. We said that's got to be 0. Okay, so that's it. So the cosine piece gone. So G is now just the sine piece. There's a constant in front of it. I actually still don't know what C2 is, because remember, all I'm saying here is, well, I know I don't want to make C2 always 0. So actually we failed at coming up with what C2 is. But we did gain something valuable here, which is that we actually figured out how much sigma has to be, or well, actually square root of sigma, which is actually kind of important. This has been a bit of a mystery to us the whole time, but it's actually no longer a mystery. The only way for us to get a meaningful solution is to have square root of sigma be of this format. So if I'm collecting together to say, so what did I actually just come up with here? The g of x that's going to work is this one, but actually there's a whole bunch of these that work. Anytime sigma is any one of these, you'll get a solution. All right, so my conclusion is, I'll write this on the next slide too. So g of x, which is, and now I'm just going to call it a constant instead of c1 and c2, since we got down to just one constant anyway. So g of x, which is equal to some constant times sine of, and now instead of square root of sigma, I'm going to fill in our discovery, which is actually really important. Right, so here's our guess. Right? So sigma, which turns out to be that, these all work. When n is any whole number you can think of. Okay, so in fact, right, we usually label these, and now if you allow me, you can squeeze this into your notes, right? I'll call that maybe G subscript n, because I'm going to sort of say that that's, you know, since I have this works for any number that you want to put in there, Gn, maybe I have some constant that depends on n. Although to be honest, we're going to sort of recycle that. But these are all solutions. I don't know what Cn is just yet, but I know that the main piece of it, the actual functional piece, is this sign contribution. This is our least favorite thing in the world to look at, right? I mean, this is not great, that I have this n pi over L. I mean, if I could just erase that, I would, you know, because that would at least make it a little more digestible. Oh, okay, it's sine. But that's good enough, right? So just think about that and say, oh, okay, so it's a sine function, right? Okay, so we're halfway there. The other half is faster, I promise, right? So just so we're not completely losing sight of what the hell we're doing, let me just do the mid-crazy derivation throwback. Oh my goodness, many slides. So here was our guess. We've done now an awful lot of work in order to conclude several things. One, the G's, plural, that work are that last thing I just wrote down. They will all be functioning solutions. I don't know the H yet, but I at least figured out the appropriate G's, or G's, that are going to make up my solution. I also made an important discovery along the way, which is that the only sigma that works are these. Right? So these are the only sigmas. Yeah, okay. That work. That's actually kind of good, right? When we started this process, we said sigma is some random, or not random, well, but sigma is a constant that I don't know who it is. I still don't know exactly who sigma is, but I at least know for sure it's numbers of this format. A whole number times pi over whatever the L for your problem is. So we're chipping away at this, right? We're making decent progress here. But the big piece that's still left is, how about the h piece? So we've done all this stuff to figure out who the g is. Along the way, we figured out who sigma is. And our last thing we have to do is figure out who's h, or what's h. All right, that's going to come pretty directly, though. All right, so that's a big one. So those are our g's that are going to work. Here's our sigmas that are going to work. So how about the last piece? And I have no idea what numbering I'm even remotely possibly doing right now. Okay, I don't know. So I'll just write a sentence for you. All right, so we have G, we have sigma. How about H? Okay, so let's see if we can work our way through what H is. Now, I left us a little bit hanging. So what's our ODE? So our ODE for H, I'll copy it down from an earlier slide. Here's the ODE. Is plus sigma squared alpha. Oh, sorry, sigma alpha squared H equal to 0. Now, I don't have an initial condition for this. I don't know what H of 0 is. Now, if you think about it, I do know the initial temperature across the rod, but H of T is not the temperature across the rod, it's the T component, or the T contribution. So I don't actually really know how much H of 0 is, which means while I was kind of hopeful, let me fill in so as to not leave us in the lurch. We were able to fill these two guys in by doing some, an observation. This one, we're not going to fill in. But as it turns out, we're going to be perfectly happy. What happens when we don't have an initial value for an ODE? It just means you can't solve for C1 and C2. Well, this one's just going to have a C. But that's all right. We're going to be happy enough with a general solution here. All right, so let's get to this finally. So, okay, we want to solve this. Well, remember, this is just a number. And in fact, I'm going to fill in what it is, since it'll be helpful in a second to have it as such. Maybe first thing I'll do is I'll move it to the right side. So I'll just move that over there. But now we just discovered in the last problem, one of our big discoveries was right here, that square root of sigma is n pi over L, all of the n pi over L's, where n is a whole number. So of course I didn't write it down, but we all know that that would of course imply that sigma is that stuff squared, right? I mean, I'll just jot it here. It's not even worth mentioning, but of course, right, that obviously means the same thing, or it implies that sigma is just the square of that stuff on the right, n pi over L. Well, that's what I'm going to use right now. This sigma, I'm going to replace it with n pi over L. A square of that, right? So sigma is really n pi over L squared, alpha squared, H of T. Okay, that's just by definition of what we discovered sigma to be, or the square root of sigma actually, but I squared it. Now, of course, the benefit here is that everything here is squared. So this is all just ease of notation. You could pull those all together, right, because they're all squared. That's why we call it alpha squared. I mean, oh my goodness, that was a long time ago that we maybe pondered for a minute. Why the heck did we call that constant alpha squared? Well, here's finally a good justification, is because then it's squared just like the rest of the terms that are going to be part of our solution. Okay, now don't let this intimidate you. This is a number. Okay, so if I wanted to solve this, this is the separation of variables problem. This is dH dt equals, get rid of my, equals this number, this crazy ass number, times h, right? And what do I do to do this? I separate and integrate. So I put the dH probably on the left, put the h on the left, so dH over h equals, once again, this crazy number, times dt. You integrate both sides. And over on the left, you get ln of h. And on the right, of course, you just get that with the t tacked onto the end. All right, so I'm going to pull this up. So, of course, over here you get ln, which then when you undo the ln with the e, we're going to end up with, well, I'll do this in steps, right? So I get ln of h. And over here, of course, you just get that stuff times t plus an integration constant. So what do we do to solve this now finally is we can say, all right, so h, if I e both sides, of course, we remember that the constant comes back down in front, and I get e to the that stuff, t. And this works for n equals 1, 2, 3, and so on. Oh, gosh, sorry. So I'm actually going to call that h subscript n to say all of those. We were trying to find a solution for h. Well, we found a whole family of solutions. All of those guys work. And if I want to, call that Cn. Okay, so believe it or not, we're done. So let's recap, one last recap, and then I'm going to write it all down. So we were trying to figure out a G and an H that make this work, that make our guess work. And after about an hour of work that we've just done, we've come up with, actually, a whole bunch of G's that work and a whole bunch of H's that work. So, but of course they're operating under the same sigma, right? So why did I get a whole bunch? Because sigma turned out to be possibly many options. So for each option of sigma, I get a G and an H. Now, of course, I have to multiply them, right? That's my setup here. So any of those G's paired with the buddy over in H world is going to be a solution to this ODE, to this PDE. All right, so let's pull this all together. Both of our solutions had constants in front, as we do our little tour here of slides, right? Our G's had a constant in front, and so did our H's. Okay, well, we don't need to kill ourselves here. You don't need a constant from the H and a constant from the G because we're multiplying them anyway. So I'm going to rewrap those into just a new constant, right? I'm not going to do both of them having CNs. I just make up a new constant, which I'll again call Cn. So pulling this all together, we finally get, so now as a solution to the PDE, remember that was U, now we've got a bunch of them, so I'm going to subscript this in order to say, normally I would have probably just said this, right? U of x and t is blah, blah, blah. But since we ended up with a little bit of an embarrassment of riches here, we actually ended up with a whole bunch of solutions. So let me subscript those as well. So UN is going to be a solution as long as it's the product of the GN that we discovered with the HN that we discovered. So I'm just going to reproduce those here for you. So the H piece, I don't know why, but usually the H piece is written first, so I guess we'll follow typical convention here. So that's the piece with t's in it. The piece with x's in it turned out to be the sine function. And both of these actually had a constant in front, so rather than doing two constants, let's just relabel and reimagine a fresh Cn constant in front of that. So we get that these, and just a reminder, for n equals 1, 2, 3, and so on, are what are called the fundamental solutions to the heat equation. Right? In other words, they're all solutions. Okay, so this is where trumpets and angels and all of that should start occurring to us, that we've actually done it. So we've actually solved the heat equation from scratch. Took a while, but this is the solution. Now this is probably of our long time together solving DEs in general. I mean, we thought we saw some pretty bad shit. Well, this is worse than all of that, probably, right? I mean, just look at this. I got pies in it. I got N, okay, I mean, I got a lot of stuff here, right? But try not to get too bogged down with the ugliness of that and the ugliness of that, and let's just squint for a second. So who is this? This is sine. Oh, hey, we know who sine is. That's one, that's sine. And what does an E do to sine? Well, this is positive, isn't it? Right, because I'm squaring it. And T, that's time, so that's positive. So this exponent up here is always going to be positive. So e to some the exponent, this is going to be positive, but there's a negative here, right? So it's always going to be negative. And what happens when I allow time to go on is this just becomes more negative. In other words, bigger, but negative. So of course, what does this do to sine? Is it says, well, sine's going to do this, but it's going to head towards 0. So if you graph any one of these u's, they all look like this. So it's not so scary, right? So I'm trying to hopefully convince you we haven't created some alien creature here that's like unattainable and just, you know, what the hell is that? It's this. Right? So the solutions to the heat equation are waves that all look like this. Okay. I mean, I'm being a little cute here in the sense that, of course, I have x's and t's, so of course this is actually a 3D graph rather than a 2D graph like I just drew. But essentially this behavior, at least, right? I'm trying to make this seem a little less scary for a minute here, right? As time goes on, this piece is going to head towards 0, and as x goes on from left to right, this is just going to wave at you. So as time goes on, at least, what's happening to my waves is my waves are decreasing, right? So I'm going to erase this just because it's not an official sort of not a super official answer, but just from a human perspective, think about that, right? That is sort of what these guys are all looking like if we could draw a 3D graph and flatten it out. They would all be vanishing oscillators. It would be how I might describe the graph I just erased. Now, if you think about it, oscillation makes sense. I think we say heat travels in waves, just like a lot of other substances. So it kind of makes sense that there should be a wavy sort of pattern to this. But a diminishing one hopefully also makes sense because, of course, unless I'm applying continuous heat to this, it eventually is sort of dying out. Right? So there's some reasonable things that I know you're looking at this and just being like, so what the hell are we doing with this? What problem are you going to ask me to do where I have to use this? So sure, we'll get to that, right? But try to have a little bit of appreciation that this, while ugly, is sort of the bread and butter of any sort of ODEs that we've looked at. It's some E with some trig, right? Okay, so how are we doing on time? All right, so I will, of course, do an example or two of using this. They take a little bit of time to get, well, they don't take that long because I'm going to do easy examples, but I'm going to save those for the next video. So let me just finish with a sort of a nice then summary, I think, of this and how we are going to view these guys coming together. So these guys individually or collectively as a collection are known as the fundamental solutions. So then the general, right, we're familiar with that term, right? The general solution of the heat equation. Just like in ODE's class, when we came up with solution or solutions, we were allowed to take any linear combination of our homogeneous solutions, right? So, and we'd still end up with a solution. And if we took all the combinations of our homogeneous solutions, we ended up with the full general solution. The heat equation is homogeneous. I have the UT term, and I have the UXX term, And that's it. I don't have any other pieces. So it is also homogeneous, or can be considered homogeneous. So the general solution of the heat equation, now I will write this as u of x and t, is simply any linear combination of these guys, of the UNs. So I'll write this down one last time, but I'm going to do it with the sum notation here. So you can have any, I'm just going to copy down UN just one more time. It's so much fun to write. Right, so the general solution says, hey, take any combination of these UNs, and they will all be solutions. So taking 6 of one and 5 of the other and -6 of the next one and whatever numbers you fill in for Cn will give you the particular one that you wanted for your specific problem. Okay? So what's left, so maybe this gets the big box, right? So that describes the general solution, right? All the solutions to any heat equation look like this. So what remains about an actual example or a specific example? Well, not much, right? So what are we going to have to figure out when we go to do an example problem in the next video is how much are these C's and which of them do I want? Now, we haven't had that freedom before because we've been left, we've just had C1 and C2, which means we haven't pondered too carefully like, gee, do I want C1 and C2 or just C1 or just C2? Well, who cares? Throw them both in. And if one of them turns out to be 0, great. But in this case, you have infinity options of who you might pick. So we are going to have to be a little bit more clever about saying, oh, all right, so for a specific problem, which ends do I even want? I don't think I want infinity of them. Maybe I could get away with just a few of them. And of those ends I picked, what are the proper C's that go in front? And if I can do that for some simple examples, which we'll do next time, I could actually say that I've found a real solution, a specific solution to an actual specific heat experiment. All right? Okay, so that's for next time. So tuck this all away. Hopefully, 90% of that made sense, and you have some good ideas about where these things came from. As usual, right? I will probably ask you to do some. I already left you some ideas about. I might ask you to show this or show that, and maybe to explain parts of the derivation and things like that. This section is going to be light on actual problems that we're going to do and heavier on techniques and derivation. So while we will eventually be able to do some computational problems, a healthier chunk of what you'll see on the next exam will be asking you to explain some details and do some variations maybe of these things. So give this a thorough rewatch if you need to, in order to hopefully understand most of the steps that we took to get here. Okay, so hopefully this was all right. Have a good. This is the Thursday video of this week, so have a good weekend. Eventually there'll be some problems for you to try with these, but we really need to kind of get into a first example, which we'll do next week.